I didn't get chance to ask him. But anyway, tomorrow I have one day with me. Okay, so tomorrow in the first hour itself, maybe I'll call him and ask.
Sir, actually, I do not know yeah, last semester, Sangwan sir kept the mid-sem of sustainable manufacturing as open book,
Hmm.
as open laptop actually, and
Hmm.
then I don't think so. He talked to Dasgupta
See,
sir.
what happens, Sangwan sir himself was a HOD long time before.
Yes, sir. Yes, sir.
And he's a very senior professor.
Yes, sir.
In
Yes, sir.
fact, sometime he's above Das Gupta sir also in many administrative works.
Exactly, sir.
Okay, so he need not to take even permission, I think.
All right, sir. Then maybe you can ask him
Yeah.
tomorrow morning.
In fact, if we want permission and for any special case, we'll speak to Sangwan sir, Das Gupta sir, like that.
Yes, sir. Yes, sir. Yes.
Yeah.
All right, sir. You can confirm it to us. Otherwise, we'll have to print the
No, no,
slides.
I don't think so. I will put you guys in that because anyway, you have to spend a lot for printing.
Yes, sir.
And
Exactly, sir.
something is done, I will see. Okay.
Yes, sir.
Okay. So recording has started, and I'm. Let me check. I am sharing. So till now, what we have seen about the two things are there. Composite materials. They are known for their high stiffness and high strength. Okay, and in stiffness, uh, uh, we call it Young's modulus when we have pure metal or non-metals, and we are very comfortable because or we need to have only one value of E for each material. But for composite, okay, we have a number of values of like these different types, different values of E, means stiffness along different direction. But as we are dealing with two-dimensional lamina only, two-dimensional lamina, okay, where we are assuming that the thickness is very, very less. So we are just looking into two cases. One is the Young's modulus in the x direction, Young's modulus in the y direction. Then I have the shear strain terms like G12. Then I have nu 12 and nu 21. These are the two, three things we are looking at. But when we, in the next, after your examination, when we will be looking at the three-dimensional system, okay, where the loads are applied in all the directions, okay, then we will have some more terms like what is E11, then E22, then E33 will come, okay, and then your Poisson's ratio will also be very different, nu 12, nu 23, nu 32, 31, like this, okay, and G will be also like this, G12, G23, and G13. So this is for three-dimensional case. So we will see all the things, okay, in much detail after that once we are done with the midsem. So till now we have seen different methods to find the value of Young's modulus, okay, and we saw some of the limitations and shortcomings of the methods also. Then we move to strength. That what is the strength of the composite material as a whole, ultimate strength, okay. Like say these are the different types of loading that if it is shown here, the fibers are oriented like this, okay, that is fine. So if the load is such that it is lying along the fiber direction, okay. What is this means? It means that the fiber is parallel to the load, or load is parallel to the fiber direction, like this one. Okay, this is called as your longitudinal loading. Okay, and tensile in nature, longitudinal and tensile in nature. Here also it is same, longitudinal but compressive in nature. However, if your loads are applied at 90 degree, these are the two extreme cases. 0 and 90 degree are two extreme cases. In between, we could have a number of cases like 15 degree, 35 degree, 40, whatever the number you define. So the loads can vary based on this angle. Okay. So the two extreme cases we are taking. So what happened? It is the in that. So what is happening here? The fibers are oriented in this direction and the load is at 90 degree. This situation is called as transverse loading. Okay, and that too again in transverse loading also I will have transverse loading with tensile mode. okay, in tensile loading. This is transverse loading in compressive manner. You see here, it is how it is compressing at this end, okay, and it will be elongating. These are two. Another thing is the shear loading, okay, where you don't have any direct stresses, means normal stresses are zero, and you have shear stresses. So this will cause something a deformation like this at the later stage. So these are the different things. So what we I when we started looking at this, so at each cases, for each case, okay, the composite material will have a ultimate strength, okay, means if you are pulling the composite material in the longitudinal direction and that in the tensile mode, then it will have a maximum value of longitudinal stress in the tensile direction, that is UTS of this one. But the maximum stress in the longitudinal direction along the in the compressive mode will be different because it is a composite material, okay. So these are the different types of stresses: longitudinal tensile strength, longitudinal compressive strength, transverse tensile strength, transverse compressive strength, and in plane shear strength. So what we have done till now, we looked at these three, first two three, and we found as buckling plays a very important role in this case, the second one, and the mathematics was very complex. Even if we directly jump into the final expression, using those expression is really very tedious in a examination, in your examination or like that. So we decided that we will not do any problem on this one. Though we discussed that what are the types of loading we discussed, but to solve the problem in just 1 hour or half an hour examination, it is very difficult. So we will not look into this. So we will not ask any problem on this one. What is the situation? Longitudinal compressive strength. I will not ask any problem on this one. However, for these two cases, the equations are a bit handy. Okay, we can work out on the equation and substitute the values and see that what is the longitudinal tensile strength, means this situation, and transverse tensile strength for these two things, okay. Now these two things were remaining for us, okay, transverse compressive strength and in plane shear strength. These two things were remaining for me to show you. So once I am done with this, all these things, so then we are done for our midsem, okay. Up to this much only you will have your midsem examination. So what you have to see what are the how to find the stiffness value and strength values. This will come into your numerical parts for your numerical, okay. And some of the conceptual questions I may ask in 2 marks, okay, which already I have told you and discussed in the class, but you need to think a bit. Those will be some related with the composite also, composite only, theoretical part of composite material. Maybe some I will ask some reasoning type of thing to you. Few questions, not much. No, it's not going to be a deciding. It's not going to have a large impact on your marks, but at least like if the exam is going to for 25 marks, so mostly I will 15 to 20 marks I will ask your numericals, okay, and some 5 marks around you will have a very good reasoning questions where you just need to think, okay, and then give me an answer. So here, so we will do like that. So these are the two things that I had to tell you, and we have very limited time, so I don't want to hold you guys here. We will just look at the what how to find the transverse compressive strength and in plane shear strength of a composite unidirectional, okay. Here I'm doing with the assumption that fibers are oriented only in one direction. I don't have a cross fibers like this one, okay, like cross fibers are like this, okay, matte fiber or any other orientation of fibers are there like this, double multi-layer fiber. No, my assumption is only linear fibers are there in one direction like this one. So in that scenario, so this is called as a unidirectional lamina, means where you have fibers are oriented only in one direction. Unidirectional lamina is thin sheet of fiber, thin sheet of composite material, two dimensional in nature, okay, like this one. So my voice is audible to you,
Yes, sir.
okay. So let's see, let's finish the thing, okay. So transverse compressive strength, okay. See, we have seen this already, that uh, transverse tensile strength. You see, fiber is in this direction, okay, and we are applying a load in this direction, and this one is the tensile in nature because it is moving away from, it is taking the material away from the composite materials like this, okay. So luckily what happens in the case of transverse loading, the equations which we already have developed and which are the valid equations for tensile strength, okay, tensile strength, in the same equation, so same equations we can use to find the compressive also. So this is a good part in this transverse loading, okay. Same thing we can use. So similar type of equations we have seen when we looked at the transverse tensile strength. So if I get so derivations are, that's for the reason I'm not putting here. So directly I am putting the critical value of my critical strength, ultimate strength which a composite material as a whole can bear is given by this formula. So what are the different parts of the formula? D and S are the geometries of your you can see here. D is the thickness of the fiber and S is the mean thickness of your composite material, like from here to here. Okay, so this is that there. Then EM and EF are the stiffness of your matrix and fiber material. Okay, and this is the ultimate is what is called as the strain in the fiber, ultimate strain in the matrix. This is the ultimate strength in the matrix. So if using the Hooke's law like this one, we have a situation like this Hooke's law. So similar, if you know that ultimate uh, compressive uh, strain of the composite material in the two direction, then you have to multiply by the Young's modulus in the two direction, then you will get the ultimate compressive uh, failure stress. Okay, this term is actually ultimate compressive failure strain of the matrix. See why matrix, we are putting more stress on the matrix, because what happens, the load is applied in this direction and fibers are moving in this direction, okay. So once the load is in the such a way, then these fibers don't have much role to play in the term in the strength, in the transverse compressive or tensile strength. So most of the load in that situation is beared by your by your matrix material. So in that case, you start having cracking of the matrix material. Okay, like this small cracks are developed in the. So just you have to remember, whenever you see any transverse loading on the composite material, means matrix will fail, and whenever you see longitudinal loading in the composite material, then you will have fiber failure. Now this could be fiber breakage, fiber pull out, or the breakage of fiber matrix interface failure. Such things will happen. Okay, so this is how you, if you know the value what D, S, E, M, E, M, E, F, and all the things, you can find the ultimate compressive strength of metric, ultimate compressive strength of your composite material, which is a function of ultimate compressive strength of the matrix material. Okay, and using the Young's modulus in the two direction, you can get the value of ultimate compressive tensile, ultimate transverse compressive strength. So then here the names are bit bigger. Okay, so you have to remember like this one. Now, another thing is that when we don't have any tensile or compressive loading, means loading in the sense when we don't have a normal loading on the structure. Okay, like this I have told you that if the lamina is like this, you have normal loads like this one, either going in the x direction or going in the y direction. These are the normal loads. So the situation we already have seen. Now we will be looking into the situation when we don't have any normal loading, but we'll have shear loading. Okay, like this one, shear loading like this one. Okay, so in that case, what is the strength of the fiber or of the composite material? So this is an assumption, okay, that not assumption, when you apply any stress, maybe it has to be tau 1 to tau 1 to when now what is called a shear stress is applied on the composite material. What is going to happen? This shear stress will cause deformation of the whole composite material. Okay, in one plane, in that plane of the like in this plane, it will cause. So that deformation of your composite material will be a function of, or we can say the sum of the deformation, or the shear deformation of your composite material will be sum of shear deformation of fiber and shear deformation of matrix. Okay. Now, if I know deformation is there. So if I know the initial length of my composite material, initial length of my fiber, and initial length of my matrix, then I can multiply with shear strain. Okay, this is what I told you. The deformation is always given. No, strain is always given by deformation by initial length. Okay, now it could be anything. It could be deformation in the with respect to shear, shear. Okay, like in that case, it is called as tau 1 2. It will be your angle by your initial length, like this one. Initially, how much that difference was there, and so this is, so if you know the strain, and then you can multiply with the initial length or thickness, you can get the value of your deformation. So I know these are the deformation values. So I'll put these equations 1, 2, 3 here. If I put these things in this one, then so what are these things? So you see, gamma 1 2 is the in plane shear strain in the composite material as a whole, and in the fiber and the matrix. Okay, so if I put all the three things there, then I'm going to get a situation like this. So this is the shear strain in the composite material, which is a function of shear strain in the fiber and shear strain in the matrix material with these terms. These are geometric factors. Okay, these are the geometric factors. Now, actually, what happens when the system is acted by a shear force? Okay, then it is assumed that the shear stresses in the fiber and the matrix will be always equal. That means if you know the shear strain in the fiber matrix and shear stress in the fiber, and then you multiply with the shear modulus of matrix and shear modulus of fiber. So what I am actually getting, I am getting this is tau m, and this term all will be tau f fiber. Okay, so these two things are equal because same shear stress is acting on fiber as well as on matrix. So these two terms are valid. Okay, these two terms are equal. This equality holds. Okay, so I can again replace few of the quantities here, like I'm getting this expression in terms of shear strain of my fiber and matrix both. So I can either bring down this entire equation in terms of shear stress of fiber or shear stress of matrix by using this equation. So here they are bringing the entire equation in terms of shear strain of matrix, like this one. So again, this is a handy equation. We can use this thing in the exam. Okay. So this is about the in-plane shear strength of the composite material. Okay. Now what happens? This thing when we looked at this one, but we know that here also that most of the shear, again in this type of loading, some part but not most. Okay, that's what mostly what happened. Shear failure in the composite material is due to the matrix failure. Why it is happening? Because you have a structure like this one. Okay, and you are applying shear load. Okay, shear load, and what happens, this it has fibers. It is true that fibers are also there, but what happens, this matrix is brittle in nature. Matrix, when you cure means you put the fiber, you were putting the fiber, and then over that you are putting the matrix material. This matrix material will be in the molten phase initially, like a liquid, hot liquid. But when once it cures means when it cools down, okay, to room temperature, it becomes very hard and it will stick very strongly with your fiber material. So but even though it is sticking very well, but it is still brittle in nature, like a hard plastics, okay. So if you apply any shear loading, then what happens if you take just a soft material and you apply shear load, or a alloy material, and if you apply shear load, what will happen? The rectangle or square become like this one, rhombus type of thing, because deformation is there, okay, it become a rhombus. But this is a brittle material, so if it becomes a, if you are applying a shear load like this one, then it will break, and this breakage will be mostly due to mostly this failure will be due to the failure of my matrix material, okay. So so directly we can correlate, because the fibers are like this one, okay. But again the fiber will be oriented like this, there will not be much more deformation or failure of the fiber. But you have to remember this I am telling, but in compressive transverse loading, the failure will be 100% due to matrix material, 100% due to matrix material. Either it is a transverse compressive loading or transverse tensile loading. But here in case of shear loading, the failure is mostly due to fiber, okay, not because mostly due to matrix material, but some of the fibers may fail also, but mostly it will be failure due to the matrix material. So shear strength of the material, of the composite material, what I am going to get here, I can directly put as this ultimate strength if I know the ultimate, because this term is constant, this term is constant. So shear stress of my composite material, we can relate with the shear strength of my matrix, and ultimate in the similar fashion, ultimate shear strength of the composite material I can correlate with my ultimate shear strength of my matrix material. This is how it works, okay. So if I know this shear strength, then no problem. You know how to write G12. It is written as tau 12 by gamma 12. Okay. So if I know the shear strength of my composite material, I can get the value of shear stress also using this what is called shear modulus or shear equation, like this one. Okay, so this is how we can get the value of ultimate shear strength. So this equation is also okay, we can work on this one, okay. And so in the exam, what I'll give you, there may be chances that I may share use few table, okay. In the table you have equations, okay, not equations, in the table you have property of the materials, okay. And then you have to pick appropriate material from the table, and then derive the equations, derive the material, like I will tell you. Maybe no need to hide anything from you guys, okay, because ultimately we are working for you only. So if you see, I have a few materials with me, like this thing. This is a very good author, okay, Professor Cow, composite material. So you see, I am referring his book only. Lot of books I refer, but I refer from his book mostly. You see how he has solved the problems, okay. Like if I will share these slides with you, so you can also go through this one. It is like this. Find the ultimate transverse shear strength of a unidirectional glass epoxy lamina of 75% fiber volume fraction. Use property of glass and aluminum epoxy from table 2. These two tables they have given, and from there you have to get the equations, like tables where it is there. Tables I will share the tables also if there is it is in the exam. Okay. So in that fashion, you have to find that. So what I am going to do, maybe that I'll give you a situation that I want a composite material which should have a shear strength this much. Okay, and then you have to see from the table that which will be the appropriate fiber, appropriate matrix material for such a type of situation. Sometimes means the problem. What I am going to ask you will be all the things whatever we have discussed in the exam, but with some tweaking. Okay, because that is required, because it's going to be an open book exam. Okay, and directly I can't ask the questions which is available here and there. Okay, this is how the guideline has been given to us, that you can discuss whatever you want, whatever the things you have discussed in the exam, you have to ask from there only. Okay, but you can tweak the questions here and there so that student can think and write. So this is what I am going to do in the today's means day after tomorrow when we will be having exam. So once so this is what I wanted to discuss with you. I will share the problems. Okay, what are the problems available with me? I will share those things with you, and then you can refer the problems for your reference, and then I will then we will meet to day after tomorrow in the exam. So but remember one thing. Okay, 15th is the exam, correct?
Yes, sir.
And 15th I think is the last day for everyone, all of you exams.
Yes, sir. Last day, but then Shaurya and Kritin have an exam at 2 p.m. as well on 15th.
2 p.m. Now, so can we meet in the evening?
Um, Sir, we'll let you know. Actually, sir, we have some assignments to submit on 15th itself.
Hmm.
So maybe 16th we can meet.
Okay,
Yes, sir.
okay, okay. Because things are there. Micro mechanics we already have done, and then we will look into the macro mechanics part. Okay, so for that I need some time. That is also a bit mathematical, and it will take time. Okay.
Yes, sir. We'll meet from 16th then.
Hmm. Okay, then I'll stop the recording. Okay, and you can just disperse, no problem. Okay, because this is what I wanted to share with you.